Hello, this video is on complex roots of arbitrary degree. So there's just one type of polynomials we'll be finding roots of. The polynomial is a variable to the nth power minus 1. So that is solving this, computing the root of degree n of 1, but computing them in complex numbers. The story is going to be very interesting. And for multiplication, the best form of a complex number to be used is the trigonometric form. So let's write our unknown root as a product of the absolute value and in earliest notation this argument bit. So that exponential to the I phi is really cos phi plus I sine phi, but we're going to use it only at the very last stage. All the computations will be done using this compact and convenient trigonometric form. So let's plug it in and compare the left and the right sides of the equation. On the left we'll have the nth power of the absolute value times the nth power of the exponential, which is nothing but the exponential with the argument n times phi. On the right we have 1. Let's write it in a trigonometric fashion as well. So the absolute value, the distance will be 1. And the argument, after all, this number sits, all of them are going to sit on the unit circle, but this number 1 is sitting here. So it's a bit squashed, but it's supposed to be a circle. So the argument is, of course, 0. And that is the equation we are solving. And as with any system of coordinates, 2 points coincide if their coordinates coincide. So we have now two equations. The first equation for the absolute values, rho to the n is equal to 1. And remembering that rho is a non-negative real number, there is only one solution. Always it is 1. So that's the place, this unit circle is a place for all our solutions. For any n, there are going to be points on the unit circle. All we need to know about them is what are their arguments, what are the angles of the direction lines or rays towards them. And that is the equation which is supposed to give us the answer. So what do we know? This argument coincides with this argument. And here's a tricky bit. Because if we just look at it literally, the only solution we will see is, not literally, really naively. The only solution we will see naively looking at this equation is phi being 0. And that is this number 1, which is of course a solution. But even for n being 2, for this degree n being 2, we know two solutions. One is positive 1, the other is negative 1. So for n being 2, we are missing one solution if we just naively cancel out n and end up with phi being 0. And that is because we are naively treating the right hand side. Well, these are two arguments, they are not numbers. They are numbers related by copies of 2 pi, so up to shifts of 2 pi. If we add or subtract copies of 2 pi, the arguments do not change, so we have to allow on the right a shift of 0 by any multiple of 2 pi. That will still be a valid equation. So now the story becomes more revealing. When we take and divide by n, we will have these answers. And these answers are going to repeat eventually when k will be large enough, but for the start they are not. So the different answers, all different answers you could check, are labeled by, say, these values of k starting from 0 and going all the way to n minus 1. The nth one will be as good as 0 because when k is equal to n, you can cancel them out, you have 2 pi, which is as good as 0. So that will be the range where all different solutions for phi will be. So let me call them p sub k. These are the arguments for my roots. And then the answer for the roots, the full answer will be, let me call those roots epsilon sub k. There will be this exponential to the I of that angle, of that argument. And now I will spell it out in trigonometric form, so that will be 2 pi k over n plus I sine 2 pi k over n. So again, with these values of k, this is the complete list of my roots. I will have as many those roots as the degree of the polynomial. And let's look at small cases. When n is equal to 2, we recover our second solution. We do have two solutions. So this is when k is equal to 0, this is when k is equal to 1. And that is it. So let's look at the next example. Let's look at when n is equal to 3. So I'll draw a different circle. I'll try to draw it better this time, more circly. Still not perfect, but okay. So here's 1. And where are two other solutions? So this time I'm going to have, let me call them again. In terms of epsilon, this is epsilon 0. This is what is called epsilon 1 for n being 2. For n being 3, I should have 3 solutions. This is still epsilon 0. Yeah, now 3 is here, and I'm looking at 0 solution, which is the beginning 1. And I'm looking at the first solution, which is with the arguments 2 pi over 3. So I have to take 2 pi and divide it into 3 equal parts. So the chunks will be like that, and these will be symmetrically placed two other roots. This will be epsilon 1 and this will be epsilon 2. Going back to the properties of these epsilons, multiplicative properties, let's just record them for convenience. So the product of two such with labels k and l is one of the least. So what is it going to be is easy to read from the multiplication rule in polar coordinates. Just using this notation, you could check that this is the root with the argument labeled by k plus l. Well, if k plus l is larger than or equal to n, you have to reduce it, so that can be recorded as a different rule. If you shift by n your label, you don't do anything to the number. So the two convenient rules for this labeling of complex roots of 1. So here's epsilon 1, which is, let's call it just epsilon for convenience. That will be epsilon 1 squared, which is the same as epsilon squared. But in our special case of n being 3, epsilon squared is as good as epsilon inverse. Well, that is because epsilon cubed is 1, and so if you multiply epsilon squared with epsilon, you will get 1, and hence epsilon squared is the inverse of epsilon. But something else we could say about it, it's the same as epsilon conjugate. And that is because when we compute, say, the inverse by the formula, we have to take the complex conjugate and then divide by the absolute value. The absolute value is 1, so for numbers on the unit circle, inverses are conjugates. That is because the absolute value of our epsilon is 1. And that is going to be convenient for what is going to happen soon. We are going to compute the positions of those points. Well, you could say that just cos of 2 pi over 3. But what is cos of 2 pi over 3? Well, you could say what it is, but where does it come from? Where does this knowledge come from? So we're going to get it independently by using some algebra. We are going to use some basic information about this epsilon and derive the answers for the cos of 2 pi over 3 and for the sine of 2 pi over 3. So what do we know about this epsilon? Well, the basic property is that cubed it is equal to 1. And the second property is that it is not this solution 1. Let me connect them all into what is going to be a perfect triangle inscribed in a unit circle. So I know that epsilon cubed minus 1 is going to be 0. That is just this equation. Also, I'm going to use a sort of standard factorization of this, which is related to the geometric series. I'm going to factor epsilon minus 1 out. While thinking of this as a variable, you could always factorize this cubic polynomial. Say variable cube minus 1 is always equal to this variable minus 1, and then the quadratic. And to figure out the quadratic, you could just put unknown coefficients, so you know that the free coefficient is plus 1, you know that the leading coefficient is going to be the square, just epsilon square, because you got to get cube with plus out of the product, so that is the only option you have, and then you just need to figure out what is the coefficient for epsilon, and please check that that has to be plus 1. So just check that if you multiply the two, you get this answer. Okay, so let's look at this factorization. Again, on the left we know that it is 0. We start with this. That is not 0, so that must be 0. Epsilon squared plus epsilon plus 1 is equal to 0. But epsilon and epsilon squared together in sum is twice the real part of the number. So that is because epsilon squared is as good as epsilon conjugate. When we take a number and we add it with its conjugate, we're going to have twice the real part. So we're going to have twice this position. What is it going? What is it now? We can say from this equation it is equal to -1. So twice this is here. That has to be halfway in between 0 and -1. So that is -half. And that is the cos of, as x-coordinate of this point, that is cos of our angle, which is 2 pi over 3. So now, using complex arithmetic, we proved that this is -half. And to find the sine, it's easy now. It's just using the Pythagoras theorem and this right angle triangle. So we know that, say for this angle 2 pi over 3, the sine has to be positive, so we have to take the positive square root of 1, which is the length of the hypotenuse, minus cosine of 2 pi over 3 squared. That is already computed, so what we're doing, we're subtracting 1 over 4 from 1 and then taking the square root of it, and when the dust settles we will be left with the square root of 3 over 2. So that is an honest computation just using complex numbers of what the values of cos of 2 pi over 3 and sine of 2 pi over 3 are. That's it. See you later.